So our last topic before we finish this part of the course. So this part of the course has been about the geometry of space and vectors. That's what we call it. And we're getting into curves, where we have motion at the end. So the last topic is called curvature, but I like to think of it as bendiness. How bendy is your curve? And in particular, you can say, well, what do we care about? So kind of an example to get things going. We want to understand how the curve is moving through space, but I have to be really careful here. When I talk about the curve going through space, I'm not actually talking about a parameterized curve anymore. I just say, look, I don't know what the parameterization is. I only have the curve. So it's like I saw a wire that's bent, and I've come along, and I'm looking at the wire. I don't know how that wire got the way it was. It could have been traveled very slowly. It could have been traveled very quickly. But I'm looking at this curve, and I want to say, well, some curves seem to be a lot more bendy. They have more bends than other curves. And I want to have a way to measure how much the curve is bending at a particular point. We're going to get to what we mean by all of this at the end of the lecture. So here's sort of the intuition. Low curvature curve, this is barely bending at all. On the other hand, here's a high curvature curve, and you can see there's a lot of movement. A lot's happening to this curve. So, okay, so how do we understand this? Again, I want to be careful here. We've been talking about the motion, but I don't want you to get caught up on saying, I want to see how the particle moves. So if I have a curve, I could travel along this curve very, very slowly. And on the other hand, I could also travel very quickly. Again, I don't care about that information. I just care about the curve. Well, how to understand this? The way we're going to think about this is to say, what's happening to the unit tangent vector? So in particular, if we go along and draw some unit tangent vectors, so I'm going to say I'm moving from left to right, I can draw some unit tangent vectors. And you'll notice on the low curvature side, the unit tangent vectors are barely moving. So if I move a short distance, the tangent hasn't changed very much at all. On the high curvature, you can see that if I move even just a short distance, I could be pointing it in a completely different direction. So that the unit tangents are wildly swinging back and forth. So they're changing quite rapidly. So here's going to be our measurement. How much is the direction of the tangent vector changing? So we're going to call that curvature, and we're going to note it by the symbol kappa. And I know that looks like a K, but that's really a kappa. So here's kappa. Okay, I'll spell it for you. Kappa. So we're going to say that this curvature is found by taking the derivative of the unit tangent vector with respect to s. Now, what is s? We talked about that in our last class. We said s is essentially the cumulative length. So this is how you get rid of time. When we did a parameterization, we said we can reparameterize in terms of how far we've traveled. So that's what that's doing. So in particular, you can think of, as I move along the curve, a certain distance. How am I moving my unit tangent vector? Now, so far, this has been a pretty not too unintuitive idea. So there's definitely some advantage to this. It works. It can say, well, if I can understand how my tangent vector is moving around, that gives me a sense of how quickly this curve makes turns. So the more that the unit tangent vector moves around, I would say the higher the curvature, the lower the curvature. Fantastic thing. It makes sense. That's a wonderful thing. Now, I've listed a pro. Could there possibly be a con? Well, there is one small, tiny con, which is it's hard to explicitly compute if I tell you this is how I want it. Because there's a lot that goes into it. We know how to find a unit tangent vector. That's okay. We've talked about that. You take the derivative, divide out by the magnitude of the derivative. But that gives it in terms of time. Then we'd have to say reparameterize this in terms of s. And we talked about how to find s. You do an integral of the magnitude of r prime, and then you take the inverse function of that. So there's a lot to do to try to actually explicitly compute it that way. So our goal in the next couple of minutes is to say, let's be smart. Let's find a better way to compute it. So we have a curve, r of t. We want to figure out how can I compute that derivative without a lot of work. We're going to need two ideas. So let's go through our two ideas. First idea is the chain rule. I can think of our unit tangent vector as being the following. I can think of it as being a function of time. Then I can think of time as being a function of this cumulative length, this s. So I have a function within a function. So capital T of lowercase t of s. So that's what I want. So because I'm talking about taking the derivative of the unit tangent vector with respect to s. So when I see this notation here, it really says I should think of my function on the top, in this case the unit tangent vector, as a function of what's on the bottom of s. All right. So the way we do this is the chain rule says, well, we go through and do it one layer at a time. Take the derivative of the outside function with respect to the next layer. So that's our d capital T, d lowercase t. And then keep going. Derivative of lowercase t with respect to s. d lowercase t ds. Now, intuitively you say, of course, this makes sense. You just cancel the dt's and everything works out. There's a little bit more subtlety than that, but that's intuitively it's not a bad way to think about it. Now these are both values. The first one is a vector, and I can tell it's a vector because this is a capital T, which means vector. The second one is a number, because here time is a number, arc length is a number. So I'm going to just say, okay, so taking the derivative of this, an absolute value, I can multiply the derivative of the two absolute values together. All right, now we're in better shape, because we have expressions for these. This first one, that's just another thing that we would have called t prime. So that's where the t prime is coming from. All right, what about the second one? Well, that's a little bit more subtle. So again, the first part goes to the numerator. The second part, well, we can think of this in the following way. If I want dt ds, it turns out that's 1 over ds dt. Now, how do I think of ds dt? How is the cumulative arc length changing with respect to time? We actually answered this question last time. We didn't know why we wanted to answer it, but we did. Do you remember how it's changing? How does the total length along the curve that we've traveled change with respect to time? Almost velocity, the speed. So the total length we've traveled changes with respect to time. That's our speed. So that is where this magnitude of r prime is coming from. It's our speed. The reason it's 1 over is because I want to have it ds dt. So that becomes this term. All right. So we're pretty good. Magnitude of r prime we're happy with. Next thing for us to tackle, how can we find magnitude of t prime? So we're going to do that next. So, second idea, find t prime. How are we going to do it? Well, we're going to start by recalling the unit normal vector. Now, last time we talked about decomposing acceleration. We said that, well, there's one part that points in the direction of motion, and that we called capital T. There's one part that's perpendicular to motion. We called that capital N. And the way you found N was you took the derivative of t and then you made it a unit vector. So we have that the unit normal vector is t prime over the magnitude of t prime. So I can say that this t prime is the magnitude of t prime times the unit normal vector. All right. Well, hold on. There's more. Let's do our decomposing of acceleration. So this follows what we did last time. If I want to find acceleration, I take the derivative of velocity. For velocity, it's speed times direction. So magnitude of r prime is my speed, t is my direction. Apply the product rule. And we see it's the derivative of the magnitude of r prime times t plus magnitude of r prime times t prime. All right. And it looks like there's at least one more line we have written down here. And that is to say, hey, there's a t prime. I can replace t prime by this magnitude of t prime times n. All right. So that's a formula. This should be a little bit familiar. I mean, certainly we talked about this idea. We focused more on the first part. So today we're focusing a little bit more on the second part. And we say, hey, there's something else we did. We talked about finding it geometrically. And so if you go back to the geometric argument, we also have this other fact, that acceleration is found by this combination of t and n, where the first part involves a dot product, r prime dot r double prime. The second part is a cross product, r prime cross r double prime. And then, of course, both terms are being divided by the magnitude of r. Now, here is the fun can you match stuff up game. And the answer is, yeah, we can match stuff up. We focused last time on saying, oh, if I want this a sub t, I can take the derivative of the magnitude of r prime. Okay, so that's great. These terms match. Now, let's look at the direction perpendicular. What's pointing in the direction n? Well, what's in front has to be the same. So in other words, this magnitude of r prime, magnitude of t prime, has to match up with this magnitude of r prime cross r double prime over magnitude of r prime. They have to match up. And now, we're basically almost there. So here we go. So the last part, again, match up what's in front of the n. We can conclude that the magnitude of r prime times the magnitude of t prime is the magnitude of r prime cross r double prime over magnitude of r prime. So we can now explicitly say, here's the magnitude of t prime. R prime cross r double prime, to take its magnitude, divided by magnitude of r prime squared, because I have to bring this down. These don't cancel, these add up. And how do you finish it off? Well, come back to what we said at the first idea. We have this expression, this part, this is kappa t. So I take the magnitude of t prime and divide by another magnitude of r prime. And so we finally get the expression, it's r prime cross r double prime magnitude over magnitude of r prime cube. Okay, good. And that is our derivation for today. Just remember, that is a 3. Okay. Well, let's try this out. Any questions? All right. Well, we have a formula. Let's try it in practice. Let's see what happens. So kappa of 0 for a particular curve. And let's hope it's not too bad. Now, I want kappa 0, so I have r of t. I'll need r prime of t and r double prime of t, because there's an r prime and an r double prime. All right, what is r prime? 1 plus 2t and 1 minus 2t, and 2. What's our double prime?
2, negative 2, 0.
2, negative 2, 0. All right. Our double prime, very simple, very clean. Now, notice what we're after. We're after kappa 0. So kappa of 0 is, according to this, magnitude of r prime of 0 cross r double prime of 0 over the magnitude of r prime of 0 cubed. Now, I should point out that you can do one of two things, and I'm kind of already hinting at the direction I want to go. So what are the two things we can do? If we look at this expression, kappa of t, I can say, look, let me just take that and solve for it as a function of t. And it is a function of t because depending upon where I'm at in my curve, some parts could be fairly straight, low curvature, while some parts could be moving rapidly, high curvature. So it does depend on where you're at. So I could solve for kappa of t, get an actual expression. It's a number, it's a value. Kappa is not a vector, it's a number. But in this case, I'll notice that, hey, if I just want kappa of 0, I actually don't have to go through and do all the hard work with functions of t. I can evaluate first and then do all these things involving cross products and magnitudes. So sometimes it pays to sort of say, hey, before I do a lot of hard work, can I actually simplify it a little bit? So this happens in particular if you're evaluating at a certain point. We'll see this a couple of times, particularly in a few quiz problems coming up. So let's actually find these vectors. What is r prime of 0? 1, 1, 2. And what is r double prime of 0? 2, negative 2, 0. Good. So if we take r prime of 0 cross r double prime of 0, that would be, taking a cross product, I, j, k, 1, 1, 2, 2, negative 2, 0. Let's see, that would give us I times 1 times 0, which is 0. J times 2 times 2, 4j. K times 1 times negative 2, minus 2k. 2 times 1 times k, 2k, but I went up, so I subtract. Minus 2 times I, negative 4i, but I go up, so I subtract negative 4i, which means I really add 4i. And 0 times 1 times j is 0j, giving us 4, 4, negative 4. All right. Now, of course, we should always be a little bit nervous to make sure we did our cross product correctly. So what do we do after we do a cross product? Yeah, you should dot. Just double check. 4 plus 4 minus 8, 0. 8 minus 8 plus 0, 0. Good. All right. That gives us hope that we did it correctly. So we're almost there. Let's see. We have to do a few other things. Other things we have to do. Magnitude of r prime is 0 cross r double prime is 0. Now becomes the magnitude of 4, 4, negative 4. Well, to do this magnitude, you can actually save yourself a little bit of work, because notice these all have something in common. What do they have in common? They all have 4. So since it's common, I can pull out the 4. I can think of it as the vector 1, 1, negative 1 that's been scaled by 4. So it's like the 4 is acting as a scaling factor. So this becomes 4 times the magnitude of 1, 1, negative 1. Well, the magnitude of 1, 1, negative 1 is pretty simple to do, because you take the square root of the first entry squared plus the second entry squared plus the third entry squared. So it becomes the square root of 1 plus 1 plus 1, also known as square root of 3. All right. So there's that magnitude. And in the corner here, magnitude of r prime is 0, which is the magnitude of 1, 1, 2. So that's the square root of 1 plus 4 which becomes square root of 6. All right, so I have all the pieces in place, and so I can finally conclude that my answer is, to the original question, I'm going to have the magnitude of the cross product, which is 4 square root of 3, divided by the magnitude of r prime, square root of 6 cubed. And we can leave it like that. We could also simplify it, but this is perfectly fine. If we don't say simplify, you shouldn't have to simplify. On the other hand, if we do say simplify, odds are it simplifies to something very nice. And it's good to check. Okay, so that found curvature at a particular point. Let's try something a little bit more. Now we'll actually find it for a function. So kappa of t. So I want the curvature for all values of t. So this will be a little bit more labor intensive. That's okay. We don't mind. So this is our curve. I'm going to call it r of t. What should we do next? Okay, find r prime. So r prime will be 1 over t, 2, 2t. 2t or not 2t? That is the question. All right, second derivative. Negative 1 over t squared, 0, 2. All right, so, yeah, I forgot the square. Thank you. Negative 1 over t squared, 0, 2. Good. Now, we really have two next steps, and we can do them in more or less any order. The two next steps are find the cross product, and then its magnitude, and we also have to find the magnitude of the derivative. Let's do the magnitude of the derivative really quick. Hopefully that's nice. So magnitude of r prime of t, that's going to be the square root of 1 over t squared plus 4 plus 4t squared. Okay. Now, if this had been a nice problem, what would we hope to be true? If it was nice, we'd hope that the inside was a square. Is it nice? Wow, you guys are optimistic. I fear that when you go out into the world and you go to your physics classes and engineering classes, you're going to be, wait a second, everything worked in calculus. What's wrong with this stuff? All right. If it were to be a perfect square, this would be the middle term. So the end term would still be 2t quantity squared. What would the middle term need to be to make it work? Let's just sort of convince ourselves. Because I see a square here. I see a square on the end. What would the middle need to be? 2 times the two pieces. So here it'd be 1 over t, because I'm thinking this as 1 over t squared. And then 2t, because I'm thinking it as 2t quantity squared. And the question is, does 2 times 1 over t times 2t equal 4? And it does. Wow. Cool. So this really is 1 over t plus 2t quantity squared, square rooted. So it is 1 over t plus 2t. Good. Well, the log of t makes it have to be t is positive. So I know I've made everybody paranoid about absolute value signs, which is good, because someday a teacher, probably not me, I've already done it, but down the road, will be like, "Mwahaha, I'm going to catch these students." Little do they know that they've gone through the good calculus class, and you won't be able to be tricked twice. Okay, so that's magnitude of r prime. Well, that means our next step has to be, we've got to tackle that cross product. Okay, so r prime cross r double prime. I, j, k, 1 over t, 2, 2t, minus 1 over t squared, 0, 2. Okay, good times ahead. All right, so again, even if there's a function of t, you don't change the rule. The rule is always the rule. So we just go ahead and do the cross product like we would anything else. So we get I times 2 times 2, that's 4i. J times 2t times negative 1 over t squared, which becomes 2 over t, and subtracted. So minus 2 over t j. K times 1 over t times 0? 0. And because I went this way, I add 0. Now start going up. Minus 1 over t squared times 2 times k.
Minus 2 over t squared.
It would be minus 2 over t squared times k. But because of the direction, I'm going to subtract it, so it will end up being a positive 2 over t squared. 0 times 2t times I. 0i. Because of the direction, I'm going to subtract it. A little bit of 0 humor. Okay, all right. 2 times 1 over t times j.
2 over tj.
2 over tj, but because I went up, I'm going to subtract. So, putting this all together, we get 4, negative 4 over t, and 2 over t squared. All right. If we were paranoid, what would we do? Dot product. Does it still work with functions? Yeah, it works with anything. 4 over t minus 8 over t plus 4 over t. That's 0. Negative 4 over t squared plus 0 plus 4 over t squared. Also 0. Good. Good. Now, what's next? Magnitude. Okay. So feed this into the magnitude. So we're going to take the square root of, then let's see, what do we have? Why don't we make it nice on ourselves? You know, we are good people. So before we find the magnitude, let's do something to make it clean. What do I mean by make it clean? What do they have in common? Let's pull out common stuff. Because just like I pulled out the 4 over here somewhere, yeah, I did it over here, I can always pull other stuff out. So what's some good stuff to pull out? 2 is a wonderful thing to pull out. What else would be good to pull out? Yeah, the over t squared would be good to pull out because I don't like fractions. It's a weakness of mine, but I think it's useful to pull them out because the fewer fractions you have to deal with, the better it is. So 2 over t squared. If I pull that out, what's left in the first slot? 2t squared. In the second slot? Negative 2t. In the last slot? 1. Okay, so we take the magnitude of this. The 2 over t squared in front becomes 2 over t squared. It still stays the way it is. Then we're going to have the square root of 2t squared squared plus 4t squared plus 1. All right. Whoop, I'm way down. I'm off the page. There we go. All right. Well, what would be nice?
There's a square inside.
It would be lovely if there's a square inside. Notice that 4t squared is actually the same as 2 times 2t squared times 1. Now, why do I point that out? Well, I have a 2t squared in the front, and this 1 is actually 1 squared. So it is a perfect square, almost as if it had planned to be that way, because they had planned it to be that way. So this is really 2 over t squared, and then I have the square root of 2t squared plus 1 quantity squared, so that becomes 2t squared plus 1 after you take the square root. Okay, so that's the magnitude of r prime cross r double prime. So we're now ready for kappa. So what is kappa? So kappa will be this magnitude we just found, 2 over t squared times 2t squared plus 1, divided by this that we found before, which is 1 plus 2t squared over t. All right. Now, what have I forgotten? Yes, I forgot my cube. Even after I put an exclamation mark here, which of course the mathematically minded person will say, is this a 3 that you're really excited about? Or is this 3 factorial? No, it's just a 3 I'm really excited about. It's like, yay, it's a 3. All right, I'm running out of space on this page. But I just want to say, could we simplify even further? Yes. Yes, we can. All right, we'll make a little note here on this piece of paper on the side. So let's just see how far we can go with our kappa. So we have a 2 times 2t squared plus 1 over t squared. That's the numerator. This denominator, I'm going to write this as 2t squared plus 1 quantity cubed and a t cubed on top, because I'm flipping it. So I'm bringing it up and flipping it, and then I cubed everything. And now what happens? Get lots of cancellation. So we have things like the t squared goes into the t cubed. You got a 2t squared plus 1, getting rid of one of them. So you end up with something pretty clean. 2t divided by 2t squared plus 1 squared. So that is the curvature, about as clean as you can get it. And that's pretty clean. That's pretty clean. All right. So that's an example. I think that one might come from an old exam or something along these lines. We've asked things like this before. All right. So that's curvature in 3D. But of course you can say, what happens in dimension 2? There's a lot of questions. You can say, well, yeah, but what about dimension 2? Now, in that case, if I'm in dimension 2, I have some sort of curve. And it's a parameterized curve. It doesn't have to be a function. So I can have something doing some sort of crazy loop-de-loops. All right. So this could be possibly what the shape is. Now, what do I have? I have a parameterized curve. So this is my r of t. And I can describe it, since I'm in dimension 2, I can really say secretly, I'm going to put it into dimension 3. So I do it by x, y, 0. I add in that last entry of 0. So I can always put anything in dimension 2 into dimension 3 just by adding enough. R prime of t, well, that's x prime, y prime, 0. R double prime, x double prime, y double prime, 0. And now apply the formula. So you get the magnitude of r prime cross r double prime over the magnitude of r prime cubed. The denominator is nothing surprising. Now, if you look at the numerator, you might say, wow, that's a really simple expression. You'll notice it has 0 and 0 in the first 2 entries. I want to try to convince you that, at the very least, it should be absolutely true that the first 2 entries should be 0. Can we think about why? Well, if I'm in the plane, what's true about r prime? Where does r prime live? Or where could it live? It's in the plane. It's in the xy plane. Because of this fact that there's no motion up and down, it can be put into the xy plane. Where is r double prime? It's the same reason. I can set it inside of the xy plane. So both r prime and r double prime are in the xy plane. And if you cross 2 vectors, what's true about the direction? Has to be perpendicular. So if I start with 2 things in the xy plane and I cross it, I have to get something which is perpendicular to the xy plane, which means it has to look like 0, 0, something. And it's not too hard to figure out that the something x prime y double prime minus x double prime y prime. Okay, so that's what it turns out to be. And now it says, well, let's just do a quick example. Suppose I have the curve y equals x squared in the plane. So what do I have? I come to the plane, I draw y equals x squared, which we've done numerous times. There's my y equals x squared. How do I find the curvature? Well, I want to find a parameterization. Do we have a nice parameterization for the curve y equals x squared?
Yes. We just let y equals t.
Like sine t, cosine t.
Well, sine t, cosine t would be a circle, not a parabola. The easiest way to get a parameterization is if I have a curve of the form y equals f of x equals t, y equals t squared, which is x equals t, y equals f of t. And that's a parameterization. That's a freebie. Now, do I have to use this parameterization? The answer is no. Because curvature doesn't matter on your parameterization. It's about the curve. It doesn't matter how you move on the curve. So why pick this one? And the answer is because it's easy. That's why. You should always pick the easy one. All right, so according to this, curvature, well, we should figure some things out. So there's x, there's y. What is x prime? It's 1. X double prime? 0. Y prime?
2t.
2t. Y double prime?
2.
2. So we have x prime y double prime, so 1 times 2, minus x double prime y prime, 0, over, now downstairs we're going to have x prime squared, so that's 1, plus y prime squared, so that's 4t squared to the 3/2 power. So this is 2 over 1 plus 4t squared to the 3/2 power. All right, so that's not so bad. Now, I don't encourage you to memorize this formula. Memorize just one formula for curvature that works and say how to adapt. You're much better off. It takes fewer brain cells. Let's ask a question about this answer, though. Where is the parabola most bendy? In other words, when is curvature large? So there's only one t, and you have to think about what is it doing. As I make t larger, this whole expression in the denominator gets larger, which means the value gets smaller. It doesn't matter whether I'm going positive or negative because I'm squaring. So to make it the whole expression be large, we should choose t equals 0. Well, does that agree with our notion of parabolas? Is it most bendy at the very bottom? And hopefully, if you've seen a parabola, you're like, that sounds true. That sounds true. Now, we're not done yet. We have a few minutes, and that's good because I said there's still one idea. Where does this motivation for curvature come from? So let's do one other special case in the plane. We're going to look at a circle of radius r. Now, if I have a circle of radius r, it's easy to parameterize a circle of radius r. You use cosine and sine. That's how cosine and sine can be interpreted. They can be interpreted in terms of moving on a circle. The r in front of the cosine and sine, that corresponds to the radius. It's a scaling factor. All right, well, so I have these expressions here. So let's work out what will happen. So r cosine t is my x, r sine t is my y, and I have this here in the plane. What is x prime? Negative r sine t. The r is a constant, so don't worry about, like, I have to use a product rule. R is a constant, so I can just only need to worry about the derivative, the trig part. Second derivative, negative r cosine t. Okay, do the same thing for y. What is y prime? R cosine t. What is y double prime? Negative r sine t. So far, so good? I hope so. All right, so here we go. Kappa of t will be equal to x prime y double prime. So x prime times y double prime gives me what? R squared times sine squared minus x double prime y prime. Okay, so if I take x double prime times y prime, what do I get?
Minus r squared cosine squared.
I get r minus r squared cosine squared, but I'm going to subtract that, so it'll become a plus r squared cosine squared. And that's actually an absolute value there. Divided by, now I'm going to take x prime squared, which is r squared sine squared, plus y prime squared, r squared cosine squared. You can take that to the 3/2 power. Okay, let's simplify. In the numerator, I can pull out the r squared. I have sine squared plus cosine squared, which is 1. So I get r squared upstairs. Downstairs, I could pull out the r squared. Same idea. Sine squared plus cosine squared equals 1. But notice I have to be careful here. 3/2 power. R squared to the 3/2 becomes r cubed. So we get that the curvature of a circle is 1 over r. Now that's the answer. Now a couple of things to note. Should we be surprised that a circle does not have the curvature depending on time t? No, we shouldn't be surprised. Why? Because a circle, if I look at this part of the circle here, it looks the same as that part of the circle. It looks the same as that part of the circle. The circle has all this beautiful symmetry. So it shouldn't depend on t. But the nice thing is the answer is really clean. It's 1 over the radius. All right, so where did the motivation for curvature come from? The classical interpretation. The idea was to say the following. Just look at any curve. So for instance, look at this parabola. We have this philosophy that says the following. If I zoom in really close, my curve looks flat. It looks like a line, and we have a tangent line. Well, if you don't zoom in all the way, it's a little bit bent. You say, well, there's a little bit of a turn to it, so a small part of it looks like a little piece of a circle. Well, what circle? I need to know the radius, and the answer is you look at the curvature. So the curvature is looking at what's the radius of the circle that curve looks like if I look on a small stretch of it. Now you might say, well, that's a weird thing to do. That doesn't make sense. Parabolas are obviously the way to go. Well, we say that now because we have several hundred years of hindsight. But think about where math came from. Math evolved from ancient Greek and geometry. It came out of the ideas that started there. Now, what did they use in ancient Greek? What were the two things they could do? Straight lines. They called it a ruler. And the other thing they had are circles, compasses. So for thousands of years, everybody tried to say, look, there's straight lines and there's circles. And that's how we're going to think about things. So that was how they thought about curves. They said, hey, straight lines and circles. But of course, now we know better. All that cool stuff like Taylor series, the best part of Calc 2. All right, that's it for today. Pick up again next time.